Good morning, good afternoon, good evening, everyone. Today I'm going to talk about my paper picks for the 2022 Hydraulic Fracturing Technology Conference. A disclaimer I want to make is that these thoughts are all on my own, and these are not all of the papers that I suggest you ought to check out. There are a lot of papers that I thought were completely amazing, but there were just a few for the sake of everyone's attention span that I thought that I would share in this presentation. The first paper I'll talk about is 209145, Time-Lapse Monitoring of Interwell Communication and Drainage Frac Height using Geochemical Fingerprinting Technology with case studies in the Midland Basin. So this is a method to monitor interwell communication and drainage frac height through time based on unique geochemical fingerprint data collected from oils. Produced oils of 9 horizontal wells over 20 months and cutting samples from the vertical section of an adjacent well were collected in the study area located in Midland Basin, Texas. The 9 producing wells were 2 DSUs with 2 different well configurations, one drilled with 2 landing targets while the other with 3. Drainage frac heights and quantitative production allocation by zone were conducted by building a geochemistry-based model correlating with the produced oils back to their contributing intervals, represented by the cutting samples and their vertical depths. The probability of interwell fluid communication between each well pairs was calculated based on the similarity of the geochemical fingerprints in the produced oils of the corresponding wells. 3-target scenario generated significantly more overlapped drainage vertically and vertical well communication than the 2-target scenario. Up to 60% of the drainage frac height of the middle well in the 3-target scenario overlap with the upper wells and 20% overlap with the lower wells, while the 2-target scenario in the upper and the lower wells showed only 40% overlap vertical drainage. I strongly suggest you check out this paper in order to look at some of the technical well spacing recommendations through this technology. Next paper I suggest you read is 209138, or Counterprop Delivering Beneficial Proppant Flowback Mitigation and Improved Well Productivity, a Success Story in the Permian. This is a lab study used large-scale tortuous slot flow equipment at slick water in different proppant sizes and sequences. The model and lab study results indicated that larger proppant settled near wellbore, creating a barrier to prevent smaller proppant grains moving into the wellbore, thereby mitigating proppant flowback and generating higher fracture conductivity in the near wellbore area. An iterative, phased approach for field implementation was applied to reduce the execution risk of injecting large 40-70 mesh proppant before small 100 mesh with slick water. Multiple field trials have been executed since late 2019 in both Midland Basin and Delaware Basin. In Lower Sprayberry of the Midland Basin, the range of median uplift was 5 to 42% of cumulative oil was measured compared to offset control pads. In the Delaware Basin, proppant flowback during early production phase is an issue handled with surface sand separator equipment, and the goal for Counterprop was to reduce the time and cost of the sand separator equipment on location. Counterprop was implemented in multiple Wolfcamp developments in the Delaware Basin with no execution issues and resulted in decreased proppant production compared to similar developments, therefore allowing a release of proppant flowback management equipment from these locations, approximately 70% earlier, contributing to savings and production benefit with higher pressure drawdown allowed. I strongly suggest you read this paper to check out a new way of how we can place our sand and how to mitigate the sand flowback whenever we flow back our wells. And I thought this was an interesting paper and a pertinent paper, for me at least, when I take this back to my company. The next paper I suggest you read is 209128, or Empirical Meets Analytical, a novel case study that quantifies fracture stress shadowing and net pressure using bottom hole pressure and optical fiber. The case study will review measurements taken from 2 permanently installed bottom hole pressure gauges along with horizontal wellbore during hydraulic stimulation. The first bottom hole pressure gauge is located at the toe of the horizontal wellbore being stimulated and is in communication with hydraulic fractures created during the first stage. The second bottom hole pressure gauge is located near the heel of the same well being stimulated. The bottom hole pressure gauge at the toe of the well is used to measure the poroelastic pressure responses generated as stages completed uphole from the first stage. The optical fiber is analyzed to evaluate near wellbore and far field fracture interactions. The measurements have been integrated into a fracture simulator to calibrate far-field stress during hydraulic fracture growth. Measured stress shadowing in this pilot allowed authors to develop an equation that can be solved to estimate for net pressure. The results are aligned with measurements obtained from defits in the area. Historically, net pressure and stress shadow values have been difficult to measure with high confidence due to the various pressure losses between the wellhead and formation. Net pressure is a key for optimal cluster spacing design and a critical matching parameter for hydraulic fracture stimulation models. Small errors in net pressure matches can have significant impacts in resulting stimulated fracture geometry. This paper will detail the integration of empirical data to advance an analytical model that quantifies net pressure and pore elastic stress transfer from a hydraulic fracture. The next paper I suggest you read is 209130, or Perf Cluster Efficiency of Cemented and Plug Perf Limited Entry Completions, Insights from Logging Based Diagnostics. This is written by Cordax Technologies and Great Western Petroleum. Information about cluster completion efficiency can be obtained using conventional and well log measurements for fracture fluid mapping. Contemporary logging conveyance methods makes this information gathering practical for modern horizontal wellbores. A log-based perf cluster efficiency computational method will be presented. These conventional open-hole logging measurements reveal insights into the near wellbore region, including annular cement density, and can be used to anticipate fracture behavior. Integrating well log measurements with fiber optic diagnostics provides insight into the performance of each perf cluster and the factors controlling frac construction. This paper illustrates the recent observations about perf cluster efficiency using traditional well log measurements with new conveyance methods and summarizes the results for several cemented, plug, and perforated completed Niobrara and Codell wells within the DJ Basin. A comparison to interpreted fiber optic DAS data is included, illustrating a good agreement for perf cluster efficiency. So I suggest you read this paper to look at how perf cluster efficiency can be taken into consideration or can be analyzed using this technology. The next paper I suggest you read is 209172, or Completions and Stimulation and Experimental Design, Execution Analysis and Application for the Permian Delaware Basin Hydraulic Fracture Test Site 2. So these trials included HFTS2 operator-based plan completions, a more aggressive limited entry practices, tapered number of perforations per cluster, extreme limited entry up to or cluster spacing up to 330 feet stage lengths with ALE practices. Diagnostics included multiple wells with optic fiber and step-down tests to evaluate stimulation domain characteristics in the near wellbore region and the far field region and the wellbore region. The combination of multiple wells with the permanent fiber optic installed and controlled sequencing stimulation treatment with the placement operations enabled good understanding of the frac domains created in the wellbore region, near wellbore region, and the far field region. Evaluation of the base design completions demonstrated good stimulation distribution SDE for most applications from the optical fiber using sensing. So stimulation distribution efficiency. Extreme limited entry applications were determined not to be necessary for SDE in the Permian Wolfcamp. Tapered perf designs were not necessary for good SDE. Risks to SDE were clearly observed with the injectivity loss due to mechanical problems with the pumping operations. Risks to SDE were also observed when the stage isolation was not effective. Extended stage lengths up to 330 feet stage lengths with 10 perforation clusters were generally effective with the ALE practices. Acquiring and maintaining injection rate was critical for the higher cluster count stages. The far field region stimulation domain dimensions were generally consistent with the wellbore region dimension distributions. Significant non-uniformity was observed in the far field region at the cluster dimension resolution. There was good correlation with domain dimensions in the far field region where there was a lack of stage isolation in the treatment well, and there were staggered landing depths of the wells. So I strongly suggest you read that paper because that covers some of the findings of stimulation distribution efficiency. The next paper I suggest you read is 209171, or Parent-Child Well Relationships Across the U.S. Unconventional Basins, Learnings from a Data Analytics Study. This is written by the University of Texas. In the study, the parent-child well pairs for wells completed with the last 7 years in 9 different unconventional basins are identified using a Python code applied to an Enverus public data set obtained in November 2020. These basins include Basin, Delaware, Eagleford, Haynesville, Marcellus, Utica, Midland, Niobrara, Powder River, and Scoopstack. Our Python code also performs calculations to create necessary comparative metrics for analysis. 4 cumulative production proxies are created using the first 12 months BOE and is chosen as the appropriate metric for the analysis. Basin-to-basin comparisons are conducted and the effects of well spacing and infill timing are investigated. The study finds that, as stated in the technical literature, child well performance increases with spacing and decreases with infill timing. Apparent cumulative production at the child well completion is a better indicator of child well performance. So I suggest you read this paper to get a better understanding of some of the completion metrics that are used when investigating parent-child or primary infill well relationships. The last paper I suggest you read is 209120, or an integration of sealed wellbore pressure monitoring responses with wellbore strain and deformation measurements for frac diagnostics. The objective of this work is to investigate, develop, and demonstrate direct link between the wellbore casing strain and deformation measurements and sealed well pressure responses. The paper presents new lab experiments for casing deformation that tie directly to wellbore deformation during hydraulic fracturing and to subsequent pressure increases caused by intersections of fractures with horizontal wellbores. They show that wellbore strain measurements can be combined with surface wellbore pressure measurements to diagnose frac intersection and estimate geometry and growth rates. Casing strain experiment was set up to measure wellbore deformation caused by loads that are encountered during the frac intersection. Multiple strain gauges were installed on a joint on a 5.5-inch P10 casing radially and longitudinally, as well as azimuthally around the pipe. A load frame was utilized to stress the casing at various points along the pipe to develop relationships between load, strain, and deformation. Analytical models were deployed to compute the expected casing strain for thick wall pipes and were compared to our laboratory measurements. Numerical modeling was performed to simulate the casing strain response as induced pressure change at the surface hydraulic fractures approach intersect the wellbore. The results of the lab measurements of azimuthal casing strain agree well with fully coupled 3D numerical modeling. Sealed wellbore pressure responses calculated from the magnitude of these deformations agree well with the actual field responses. The work now allows to relate the sealed well response to quantifiable frac geometry in a region of deformation along the casing. Strain profiles from the deformation are developed and allow a direct coupling of volume change in the wellbore due to frac arrivals. They display various fracture properties required to generate observed field responses, so 0.1 to 10 psi order of magnitude. Additionally, sealed wellbore pressure monitoring field data is reported, interpreted, and explained with the help of experimental data and numerical simulations. And I strongly suggest you read this paper to get a better understanding of some of the sealed wellbore pressure monitoring impacts to what the objectives of this paper are. Thanks so much for taking the time to listen to the paper picks from the Hydraulic Fracturing Technology Conference. As usual, please be sure to like this video, subscribe so you can get more content in oil and gas and professional development topics, and please be sure to comment on the video below on the YouTube platform so I can incorporate your feedback into future videos. I listed all my handles for social media so you can follow me or reach out to me if you have any questions or feedback. Thank you so much, and I'll see you in the next video.